Good morning. After we have gone through the bridge systems, we will today go in detail into the most important and most specific structural part of a cable-stayed bridge, the stay cables. We will go through the main used different types, lock coil ropes, parallel wire cables, and in the second part of the lecture, parallel strand cables. And in addition, there's a system parallel bar cables, which is more interesting from historical reasons. Now, the modern types of stay cables used today all over the world, rather similar, are shown here. We have the locked coil ropes, traditional, mainly used in Germany, hardly anywhere else in the world. And then we have, after those, developed the parallel wire cables and parallel strand cables. Now, they are different. An important difference also with respect to cost. And you remember with me, you always hear about economy, because that's what I'm from my practical time used. I have always been in competition. So the price of anything is important for me. Now, we have here the ultimate strength for coil ropes is about 1470, parallel wire 1670, parallel strand 1870, which means for the same amount of steel, the same tonnage in parallel strand cables, we can carry more load. And that is a first indication that parallel strand cables may be the most economic, besides many other reasons, but that is a fact. Why are they different in strength? They are drawn differently. The smaller, I draw a diameter from, say, starting a 10 millimeter bar to 7 millimeters, then I increase the strength to 1470. If I go on pulling through holes, so to say, to say 6.5 quarter inch millimeter, then I increase the strength to 1670. And if I even draw thinner to 5 millimeters, which are the individual wires of a strand, then I come to 1870. Furthermore, difference in stiffness between 170, 205, 195, we'll go into detail there. And finally, we have differences in the fatigue strength. Wires are notoriously low. They have been grossly improved over the last years. And the big advantage initially for those was the high fatigue strength. Now, these are some basic advantages. We'll go into that in detail. We start with lock coil ropes, traditionally used in Germany. They consist of an outer layer of Z-shaped outer wires. Our American friends would say Z-shaped, but we stick to Z for Z. Internally, we have round wires. Some time ago, there was an additional layer of square wires, which is not used anymore. Now, these wires are helically wound. They are not straight. You see it here. They have, so to say, they are placed in lays, one against the other. So if we pull at them and the wires want to straighten out, if they were all wound in the same direction, the cable would tend to unwind. Now we have one left wind, one right wind, left wind, and so on. And so they equal out. And if we pull at such a cable, it doesn't try to unwind. But the main point is they are helically wound, these wires. Now if I pull, then the cable tends to shrink its diameter, transverse contraction, perfectly clear. And then what happens is these Z-shaped wires are pressed against one another very closely. And by that, a locked surface is created, which prevents penetration of water and so on. And that's why they are called locked coil ropes. They are coiled, helically wound, and they have a locked surface. It's quite an ingenious system, which, I repeat, in Germany works very well. In foreign countries it's hardly used because they do not fabricate these locked coil ropes. They have open coil strands and so on. They are not very good. But in Germany there is a long tradition because these cables were originally used for winder machines, elevators going up and down in, say, coal mines. And there was a big demand for this type of cable because they are helical, they can be bent rather closely. So they can be used on winder machines or elevator cables going up and down. And that was about, 95% of what were produced were for that purpose. And the, say, 5% for bridges was economically not interesting, so they could say, we'll sell that rather cheap. We make our money with the others, and that was, of course, a market advantage against the others, other type of cables who had lived from their own. That's just a little remark, but that was the politics in Germany of the Thyssen company did them. Now it's bought by Bryden in the UK, and they are now fabricated. That's where I got my slides from. Okay. Now, the advantages of locked coil ropes, they are completely shop fabricated, and they have a fixed length, of course, which permits the erection of a cable-stayed bridge by geometry. We will hear about that later, but if I know the length of the cable and the beam and the tower, then I can just put it together, and whatever intermediate loads I have on, in the end I must come out all right. Contrary, if I don't have a fixed length, I have to erect by force, which means I have to measure geometry and all that so that I come out all right. This can be a little bit easier. The disadvantages, they have a reduced modulus of elasticity. They creep because of that spherical together. They become closer if you pull them. We'll see that in detail. Of course, shop fabricated, so the complete cable has to be put on reels, heavy. For large bridges, in the tens of tons, heavy transport. And now the killer argument today worldwide, they are more expensive on the open market than parallel strand cables. As I mentioned, due to the twist, the cables straighten, the wires tend to straighten out a little bit if we pull at them. So the apparent modulus of elasticity of the complete rope is smaller than the modulus of elasticity of the individual wires. For any wire, doesn't matter in what cable, the modulus of elasticity is constant 2.05, that of steel, period. But the complete cable, on here it's a little tricky. When we say start up installing a locked coil rope, we come only to something it's stupid dimensions, just let's say 12, which is less than nearly half only of the 2.05 of the individual wires. Then, when they are installed, we stretch them, or we do it on a bench. We can pre-stretch them. So we then stretch them up to their highest service load, dead plus life. let go, stretch, let go. It stands for 3 hours. So then the wires get tightly and we get the slack out. And so then the modulus of elasticity increases from 12 to 18. Still away from 2.05, but still there. And then during the life of the bridge, this pre-stretched modulus of elasticity stands, and we end up, what I told you earlier, with something in the range of 17 instead of 20.5. That's the problem. It creeps, and it's not a real constant modulus of elasticity. Well, I could tell you stories what happened there, but we don't have all the time. Sometimes they stretched more than anticipated, then we get a sag in the bridge. Sometimes they didn't stretch at all, and then we had the other way around. And you re-stress the cables. It's a long story. Now, how do we anchor the lock coil ropes? Basically, the inside, I come later, we have normally for our big bridges cylindrical anchor heads. They can either have a thread on the outside and a support nut, or they are supported on shims. The same type can also have what we call a hammerhead. See that? The windows are closed. They just make that noise voluntarily. Huh? Okay. So the same type, but these are installed in an anchorage and turned by 90 degrees. And so that's where they are in. Another type are open sockets, I call them, with hinges in various ways. They are not normally used for large bridges. They are more for, say, pedestrian bridges and so on. And here we have a nice picture, I think, of an installed locked coil rope. This was for the Ilvrich Bridge near Düsseldorf. How are they fabricated? Well, there are big machines, rather big ones. You see them here, where the individual wires are spun, coiled under stress together. And that's an old type cross-section. That's the new type of cross-section I have explained to you. Rather large closing machines, closing the cables, the individual wires together to a cable. While this spinning, I call it, takes place, there is internal corrosion protection added. It's not a good picture, I know, but I don't have a better one. So some for the interstices, we will see. And then finally, we have to anchor the ends of the wires in a steel anchor head. We have to anchor them. Now, we have steel cylindrical sleeves here with a conical opening, and the wires are introduced into this conical opening, and then they are broomed out. Broom is Besen. They are broomed out, and then from the end, hot metal casting, so-called zamak, is poured in, which hardens. So they are cast into metal. Now this zamak is a long development. It's mainly something like 93% zinc, 6% copper, I think, and a little bit of other things. And the development went to reducing the casting temperature. Now, the zamak today has a casting temperature so that it is liquid of 425 degrees Celsius. In older times, the material had to be much hotter. And now that means if it's too hot, we have a change of the inner molecular structure of the steel wires, which means they are not as strong in these disturbed areas than they are in the regular area, which was one reason, besides other things, that the fatigue range of these lock coil ropes was rather low. Because, so to say, the base metal of the wires was hurt, its structure disturbed by too hot casting. That's why later cold casting material was looked for. We will see all that. So they are cast in, and finally, after they are installed, they are painted. So in total, we have today, and I always talk about the modern, there was a major development. We have the individual Z-shaped or round wires. They are galvanized, verzinkt. Then, when they are bundled, the little pieces called interstices between the wires are filled with a corrosion inhibitor. And finally, after they are installed, stressed, they are painted, normally 3 layers of paint. I don't go into the details, it's all in the script. It's all highly sophisticated what is used there. But that's the basic corrosion protection. Of course, it has to be watched and later to be repainted, but basically simple. And they have the most concentrated steel core. If you compare the outer diameter of this and other cables with the square meters, or the area of steel, it's all steel. You don't have any wasted, so to say, around. Now, how can we inspect these cables? The cables are the main load-bearing member of a cable-stayed bridge. They are supposed to hold on as long as a bridge, say 100 years. Now, on the other hand, they are thin, they are subject to attack, to weather in general, so they have to be inspected. From the outside, it's simple. If the paint flakes, well, we just take it off, repaint it, be done with it. But what about the inside? How can we find out whether inner wires have broken? Okay, lately 10, 20 years more, it is done by magnetic induction. There is a magnetic ring going through, and then the echo on the other side, when it goes through the wire, shows up wire breaks. For example, here, this is a printout from these magnetic induction, and from the shape of these, say, hitches here, we can say, okay, at this place an outer wire is broken, at this place an inner wire is broken, and so on. A small number of broken wires doesn't matter, and because of the coiling and the transverse contraction, after, say, 2 meters, a broken wire, due to friction, again bears the full load. That's an example from the coiling. But we must know. There were a few incidences, mainly with the old type of lock coil ropes, which I would like to share with you. Famous is the Köhlbrand Bridge in Hamburg. You see here at the anchorage outer wire breaks. We see that with the naked eye. And finally, so many wires of so many cables broke that all cables had to be exchanged. The reason were many, as always, if something happens. There's not just one. But the one reason was there was a design mistake. The anchorages were built in with the secant angle, not with the tangent. So there was additional bending. But the main point was, at that time, people were afraid that galvanizing of the wires would cause hydrogen brittleness, Wasserstoffversprödung, which could cause early breaks. So they were not galvanized. And there were some other things in addition. So the cables had to be replaced. At that time, however, the loading cable exchange, which we today apply as a matter of routine to cable-stayed bridges, same as we apply the loading bearing exchange for regular bridges. That wasn't considered, and then because we have to take out only one cable on the one side, we have a big torsional moment there, and the steel cross-section couldn't take it, let it be sufficient to say wherever a cable had to be exchanged, an auxiliary diagonal, steel diagonal, had to be installed in the box so that it was able to take the temporary torsion. Another example, Maracaibo Bridge, we'll see that later in series of cable-stayed bridges in Venezuela. Big bridge built already in the 60s by Morandi, used locked coil ropes with a saddle here on top, and many wire breaks. Several reasons. One reason, of course, Venezuela, more than 20 years, nobody looked at it or painted it or did anything, and that's a very hot, humid climate. So that is very aggressive. That was the main reason. And in addition, they made some other mistakes. It's all in the script. So then, at the end, 2 or 3 ropes broke completely. And then people took notice, oh, something is happening. The wire breaks were of no interest there, but then we were asked, and we finally said, okay, we'll replace the old ones with new ones, and then had a new saddle installed on top, and installed new ones, took out the old ones. Lately, Rhine River Bridge Flehe, built early 70s. I was very much involved, I know it well. And so it's not so old, and you see here few wire breaks, and even worse. So that also had to do, that was still the old type of cables with not galvanized in these things. Today it's all much better, of course. And now Flehe is a main artery across the Rhine River at Düsseldorf. So one didn't want to close the bridge for cable exchange. And so the cables were exchanged under traffic, which can be done one after another, but it takes a little preparation and thinking. It's quite unique. So much for the locked coil ropes. All cable-stayed bridges in Germany have locked coil ropes, except the last 2, Strelasund and what's the name at the Upper Rhine Bridge, Wesel. Those are the 2 latest, and there, with a little help of us, we came into the international sphere. There were parallel strand cables used, but for the first time. Now, from historical reasons, there are also parallel bar cables. I just mention it so that you've heard about it. Developed by Finsterwalder for the second Höchst bridge, which we mentioned earlier. He wanted to use Dividac stress bars, and what he did, he had for permanent loads these bars with a thread and a nut at the end. That's the concrete cast in. Outside he used a heavy, thick steel pipe around, and had a special bonding mechanism cast into the concrete. So the basic idea was permanent loads are taken by the stress bars, and life loads, fatigue range, is mainly taken by the steel pipe. So he tried to distinguish both loadings to the 2 parts, bars and cable and steel pipe. Very ingenious, worked, all the tests were done. First example, as I say, Höchst bridge. Now, of course, one disadvantage is because we have heavy steel pipes, we need a scaffolding to support every steel pipe first, and then put in the bars. It's a little tedious. Another was Dame Point Bridge in Florida. I remember that because I had an alternate design on that inn, and we had high hopes, but finally Finsterwalder and Dividak were winning with their parallel bar systems. And also the Penang Bridge in Malaysia uses them. 10 to 15 more, 20 years ago. I was checking engineer on that to check the bridge for new higher loads, and we found that the short cables here had, by creep of concrete, taken on much more load than they were supposed to, because they are so short and stiff. And so we then said, okay, we'll introduce bearings here to unload them, and that worked very well. So, so much for parallel bar cables, not in use anymore, they are too expensive. That's as simple as that. Now, parallel wire cables. They consist of parallel wires, 1/4 inch, 6.5 millimeters, something like that, inside a PE pipe. Between the PE pipe and the wires there is some corrosion inhibitor, initially cement grout, like post-tensioning tendons, and there is then a helix around to keep them together in a tight position, and the wires themselves today are galvanized. Now, how did that come about? Completely new development, started 1960. So now let's go here. What are the advantages of these parallel wire cables? Completely new system against, at that time, only lock coil ropes. Started in the 60s. Now it's a highest modulus of elasticity. The modulus of elasticity of the cable is identical to the modulus of elasticity of the wires. There's no coiling or anything, it's just straight wires. Of course, they don't creep like ropes. They are also completely shop fabricated and have the exact length. Disadvantages are shop fabricated, high weight, if we have to transport the full cables, and I'm sorry to say, more expensive today than parallel strand cables. Now, how did it all come about? It goes back to 1939. Professor Leonhardt, my mentor, so to say, was in charge of designing and building the longest suspension bridge in Europe, Rodenkirchen Bridge near Cologne across the Rhine River. Lock coil ropes were used as a suspension bridge for the main hangers, and he made fatigue tests and found out at that time they were extremely low fatigue strength. For a suspension bridge you don't need much, you don't need more, it was okay, but were no good. And then since then he thought about how can we improve that. And then when we had to do our office, Leonhard Andre and partner, before my time, a pedestrian bridge in Stuttgart, so-called Schillersteg. Leonhard and Andre, the founders, had the idea, now we do not use lock coil ropes, as was regular. I don't like them because of the disadvantages. And then they said, okay, we'll use BBR tendons. Now, BBR tendons anchor the wires with button heads in a keeper plate, parallel wire. And that's how the Schillersteg was built, still there, doing well. And that was the basic idea. And that was then formalized over many years. I was partly involved in the development myself later. It's basically the wires, they have this button head and anchored here in a plate, in a keeper plate, retainer plate. Later on, the development for bigger cables was how to develop a cold casting material. You remember I told you the disadvantages of the hot casting for the lock coil ropes, changing the structure, low fatigue strength. And here we have now then said, okay, we'll fill this conical anchor head, anchor sleeve, with very thin steel balls. Pour them in, rattle them, tight closure, and then these very thin steel balls, they clamp these broomed out wires. That's the basic idea. We see here the anchor sleeve, the wires, the retainer plate with the button heads. That is this situation here at the end. They are first installed, and then they are filled with these steel balls, about 1.8 to 1.5 millimeters. And if you think they're broomed out, you fill them and make sure it's tightly the balls are in. Then they clamp the wires. And that's the high-M system. It doesn't change the inner structure of the steel because it's cold. And now the difference in fatigue is demonstrated with the fatigue testing of two similar test stay cables. However, they have one difference. This anchor head is using the hot casting tarmac material, and the others use the cold casting materials of steel balls. And now we make the fatigue test. We stress them for 2 million cycles between 45 and 50% of ultimate. And then we tension them until they break. And the interesting thing, as shown here, is all the wire breaks for the hot tarmac filling take place at the exit of the anchor head. That's where the hot casting changes the structure of the steel. Whereas if we have the high-M anchors and we pull them after the fatigue, the distribution of the wire breaks is statistical over the length, over the free length of the cables, which means the fatigue strength is not diminished at the anchor heads, but the strength here is the same as over the free length. That was the idea behind the parallel wire cable development, to have the same fatigue strength in the free length than in the anchor head. Now, initially, these the outer PE pipes were cement grouted like tendons, as shown here. And for example, in this Schillersteg bridge, after 15 years, there were windows cut into the PE pipe at the upper end. It was all filled. It was still alkaline, so the corrosion protection characteristic of the grout was there. The wires were not corroded. And from these cut-out PE pipes, after 15 years in the sun, when they were pulled, these 15-year-old specimens showed the same characteristics as virgin PE as compared here. So the UV did not make any difficulties. You could also do wrong with these, and that was the picture of the Luling Bridge in the US, where I had to investigate. After 3 to 5 years, cracks occurred in the PE pipes. And it took us quite some investigation to find out why the hell, after several years, do these PE pipe crack. It has to do with internal characteristics of plastics, which are quite different. In the scripts, you find a lot of things, what one can investigate. I'm not getting it here. The idea is, During grouting, you build up a pressure in the PE pipe. You widen the PE pipe. The higher you grout, the bigger the pressure and the more the PE pipe strains in the circumference. They had overgrouted, and they had up to 8%, 6 to 8% widening of the PE pipe. And that then is frozen in because the concrete or the grout hardens, and the strain situation is frozen in. And then plastics have the characteristic in such a situation that slowly, 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 slowly they give up, and after 3, say, years, they crack. And so you have to check on site that you do not widen the PE pipe by more than 2%. Now that's simple. If you have a 200 millimeter PE pipe, it's something like 15 millimeters or so, and you can just put a tape around and see, stop. And if you do that, nothing happens. It's in the specs, of course, since then, but that was the reason over straining. I mentioned the PE pipe is UV resistant, which is a big problem with plastics. If it gets about 2% of finely dispersed soot, which is, the German word doesn't come to me, what you get in an oven when you have the black stuff sitting there, to make it UV resistant. If you carbon black, they call it here, it doesn't diminish the strength. If you have pure PE, then after a short time from UV radiation, it breaks. Coloring is a problem because PE is inert. Regular color doesn't stick. So we used tapes around, or you can bake some mixture of PE and coloring. It's possible, but it's a little tricky. Basically, to sum this first part of stay cables up, the stay cables are the main load-bearing member of cable stay bridges. Their stiffness governs the deflection of the beam and so on. The beam stiffness is much less than the stay cables. So they are extremely important for the load-bearing capacity of a cable stay bridge. On the other hand, they are comparatively thin members, say 200 millimeters, 250, not even smaller, compared with beams which are 2 meters high, and even the roadway slab is at least 20, in concrete 25 centimeters, a orthotropic deck is 300, and so on. The towers are meters by meters, so it's thin, fine members, and they have to stand up the same time as these big, so I say partly massive members of the bridge otherwise. So on one hand they have to be stiff and strong, but in addition they have to have a very good corrosion protection, because the attack on this rather thin member is intense. And I've shown you for 2 types, 3 if you want to, how it's done. We have the lock coil ropes, galvanizing of the wires, filling with some wax, petroleum wax if you want to, and painting in various layers. So it's 3 barriers. The bars is basically thick steel pipe at the outside filled with concrete, but that's not very important. The parallel wire cables, they have galvanizing of the wires, filling either initially with grout, later with some petroleum wax because of the difficulties grouting pressure on site. So that's 2 barriers, and they have the PE pipe, thick PE pipe, 6-8 millimeters around. So they have 3 barriers against corrosion. And in the next lecture we will then talk about the parallel strand cables and their characteristics, so you will have the full picture. Thank you.